guys, welcome to Matsy with me, Miss Resi, your teacher for today. So today we're going to discuss about problem solving techniques. General guidelines for problem solving. Number 1. Read the problem carefully and all the way through. Identify the goal of the problem. What are you trying to find? Number 2. Reread the problem and draw a sketch or diagram to help you visualize what is happening. If the problem involves motion or change, sketch it at different times, especially the initial and final situations. Number 3. Write down or organize the given information. Some of the information can be written in labels on the diagram. Be sure that the labels are unambiguous. Identify the diagram, the object, the position, the instant of time, or the time interval to which the quantities applies. Sometimes, information might be usefully written in the table beside the diagram. Looking at the wording of the problem again for information that is implied or stated indirectly. Decide on algebraic symbols to stand for each quantity and make sure your notation is clear and unambiguous. Number 4. Identify the units appropriate for the answer. If possible, make an estimate to determine the order of magnitude of the answer. This estimate is useful as a check on the final result to see if it is reasonable. Number 5. Think about how to get from the given information to the final desired information. Do not rush this step. Which principles of physics can be applied to the problem, which will help get the solution? How are the known and the unknown quantities related? Are all of the known quantities relevant, or might some of them not affect the answer? Which equations are relevant and may lead to the solution to the problem? Number 6. Frequently, the solution involves more than one step. Intermediate quantities might have to be found first and then used to find the final answer. Try to map out a path from the given information to the solution. Whenever possible, a good strategy is to divide a complex problem into several simpler subproblems. Number 7. Perform algebraic manipulation with algebraic symbols as far as possible, substituting the numbers in too early as a way of hiding mistakes. Number 8. Finally, if the problem requires a numerical answer, substitute the known numerical quantities with their units into the appropriate equation. Leaving out the units is a common source of error. Writing the units show when a unit conversion needs to be done, and also may help identify an algebra mistake. Number 9. Once the solution is found, don't be in a hurry to move on. Check the answer. Is it reasonable? Test your solution to special cases or with limiting values of quantities to see if the solution makes sense. For example, what happens if the mass is very large? What happens as it approaches zero? Try to think of other ways to solve the same problem. Many problems can be solved in several different ways. Besides providing a check on the answer, finding more than one method of a solution deepens our understanding of the principles of physics and develops problem-solving skills that will help solve other problems. Approximation. Physics is about building conceptual and mathematical models and comparing observations of the real world with the model. Simplified models help us to analyze complex situations. In various contexts, we assume there is no friction or no air resistance, no heat loss, or no wind blowing, and so forth. If we try to take all these things into consideration with every problem, the problem would become vastly more complicated to solve. We can never take account to every possible influence. We freely make approximation whenever possible to turn a complex problem into easier one, as long as the answer will be accurate enough for our purposes. A valuable skill to develop is the ability to know when an assumption or approximation is reasonable. It might be permissible to ignore air resistance when dropping a stone, but not when dropping a beach ball. Why? We must always be prepared to justify any approximation we make by showing the answer is not changed very much by its use, as well as making simplifying approximations in models. We also recognize that measurements are approximate. Every measured quantity has some uncertainty. It is impossible for a measurement to be exact or an arbitrarily large number of significant figures. Every measuring device has limits on the precision and accuracy of its measurements. Approximating the surface area of the human body. Sometimes, it is difficult or impossible to measure precisely a quantity that is needed for a problem. Then we have to make a reasonable estimate. Suppose we need to know the surface area of a human being to determine the heat loss by radiation in a cold room. We can estimate the height of an average person. We can also estimate the average distance around the waist or hips. Approximating the shape of a human body as a cylinder, we can estimate the surface area by calculating the surface area of a cylinder with the same height and circumference. If we need a better estimate, we use slightly more refined model. For instance, we might approximate the arms, legs, trunk, and head, and neck as cylinders of various sizes. How different is the sum of these areas from the original estimate? The difference gives an idea of how close the first estimate is. Graphs. Graphs are used to help us see a pattern in the relationship between two quantities. It is much easier to see pattern on graph than to see it on a table numerical values. When we do experiments in physics, we change one quantity and see what happens to another. We want to see how one variable depends on the other. The value of the independent variable is usually plotted along the horizontal axis of the graph. In a plot of P versus Q, which means P is plotted on the vertical axis and Q on the horizontal axis. Normally, P is the dependent variable and Q is the independent variable. Recording data and making data tables. Number 1. Label columns with the names of the data being measured and be sure to include the units for the measurements. Do not erase any data, but just draw a line through data that you think are erroneous. Sometimes you may decide later that the data were correct after all. Number 2. Try to make a realistic estimate of the precision of the data being taken when recording numbers. For example, if the timer says 2.3673 seconds, but you know your reaction time can vary by as much as 0.1 second, the time should be recorded as 2.4 seconds. When doing calculation using measured values, remember to round the final answer to the correct number of significant figures. Number 3. Do not wait until you have collected all your data to start a graph. It is better to graph each data point as it is measured. By doing so, you can often identify equipment malfunction or measurement mistakes. You can also spot where something interesting happens and take data points closer together there. Graphing as you go means that you need to find out the range of values for both the independent and dependent variables. Graphing data. Number 1. Make large, neat graphs. A tiny graph is not very illuminating. Use at least half a page. A graph made carelessly obscures the pattern between two variables. Number 2. Label axes with the name of the quantities graphed and their units. Write a meaningful title. Number 3. When a linear relation is expected, use a ruler to straight edge to draw the best fit straight line. Do not assume that the line must go through the origin. Make a measurement to find out. If possible, some of the data points will probably fall above the line and some will fall below the line. Number 4. Determine the slope of a best fit line by measuring the ratio of change of y over change of x, using as large a range of a graph as possible. Do not choose two data points to calculate the slope. Instead, read values from 2 points on the best fit line. Show the calculations. Do not forget to write the units. Slopes of the graph in physics have units, since the quantities graph have units. Number 5. When a nonlinear relationship is expected between two variables, the best way to test the relationship is to manipulate the data algebraically so that a linear graph is expected. The human eye is a good judge of whether a straight line fits a set of data points. It is not so good at deciding whether a curve is parabolic, or cubic, or exponential. To test the relationship, x is equal to 1/2 a times t squared, where x and t are the quantities measured and a is a constant. Graph x versus t squared instead of x versus t. Number 6. If one data point does not lie near the line or smooth curve connecting the other data points, that data point should be investigated to see whether an error was made in the measurement or whether some interesting event is occurring at that point. If something unusual is happening there, obtain additional data points in that vicinity. Number 7. When the slope of a graph is used to calculate some quantity, pay attention to the equation of the line and the units along the axis. The quantity to be found may be the inverse of the slope, twice the slope, or 1/2 the slope. The equation of the line will tell you how to interpret the slope and intercept of the line. For example, if the expected relationship is b squared is equal to b squared sub 0 plus 2ax, and you plot b squared versus x, rewrite the equation as b squared is equal to 2a times x plus b squared sub 0. This shows that the slope of the line is 2a and the vertical intercept is b squared sub 0.